All right, welcome. Today we're going to pull back the curtain on machine learning. Now, I know it sounds super complex, maybe even a little intimidating, but I promise you, by the end of this, you'll see it's all built on ideas that are actually pretty simple and surprisingly intuitive. Okay, let's just dive right in. First things first, let's just get one thing straight, right off the bat. Machine learning is not some kind of digital wizardry. It isn't magic. It's a tool. A really powerful one, for sure, but still just a tool. And like any tool, once you understand how it actually works, it suddenly becomes a whole lot less mysterious. And what's wild is that this, super modern field is really just the latest chapter in a very, very old human story. It's a new kind of supercharged way of doing something that scientists and thinkers have been doing for, well, forever. And that thing is extracting knowledge from data. I mean, that's really the core of it all. Just think about Isaac Newton, right? He's watching apples fall from a tree. He was observing data, just the world around him. And from that, he figured out a fundamental law of physics. Machine learning is doing the exact same thing, just with way more data and at a speed that, honestly, our brains could never handle on their own. So how do we get a machine to learn anyway? Well, it's not just one thing. It's more like a toolkit. So let's go ahead and open up that box and take a look at the 4 essential pieces you're going to find in pretty much any machine learning project you come across. So first up in our toolkit, we've got the observation. This is just one piece of data, right? A single example of whatever it is we're studying. So if we're looking at customers, one customer is one observation. If we're studying houses, one house is an observation. It's literally just one row in a giant spreadsheet. Simple as that. Okay, and for every one of those observations, we have features. These are just the individual details we know about it. So for that one house, the features might be its size, the number of bedrooms, maybe its zip code. You can think of these as the clues that the machine is going to use to try and find patterns. In that spreadsheet we were talking about, these are all the columns. Now this next one is absolutely crucial. We need a target. The target is the specific question we're trying to get an answer to. For the house example, our target would probably be its sale price. For a customer, it might be, hey, are they going to renew their subscription or not? The target is the whole reason we're doing this. It's the answer we want the machine to learn how to predict. And finally, bringing it all together, we have the model. The model is kind of the engine that does all the heavy lifting, all the actual learning. It's an algorithm, which is just a fancy word for a set of rules that looks at all our features, all those little clues, and figures out how they connect to the target. It's the recipe that turns all of our ingredients into the final dish. Okay, and this table here, often called a design matrix, shows you exactly how this all fits together. It's perfect. So each row, that's an observation. In this case, a single student. Then you see the columns for study hours and prior score. Those are our features, our clues. And that last column, final grade, well, that's our target. That's what we want to predict. The model's job is to look at this data and learn the pattern. So the next time a new student comes along, we can make a pretty good guess at their final grade. All right, so how does a model actually think? Let's look at 2 totally different ways they can approach a problem. The first one is, I think, incredibly intuitive. It's called K-nearest neighbors, or KNN for short, and it's basically built on a very human, almost social idea. The whole idea behind KNN boils down to this old saying, you are like the company you keep. Seriously, that's it. To figure out something about a new, unknown thing, the model just looks at the other things that are most similar to it and just assumes it's going to be like them. It's honestly that simple. So here's how it works in 3 quick steps. First, we have to decide how many neighbors we're going to ask. That number we call K. Then, for our new data point, the model goes out and finds the K closest, most similar neighbors it can find in the data it already has. And finally, it just holds a vote. Whatever the majority of those neighbors say, well, that's the prediction for our new guy. Now, that number K is actually a really important concept in machine learning. It's what we call a hyperparameter. This isn't something the model learns from the data. Nope, it's a setting that we, the humans, have to decide on before we even start. You can think of it like a knob we have to turn to tune how the algorithm behaves. And believe me, which way you turn that knob can totally change the outcome. And here you can see just how much that choice matters. Let's say we set K to just 1. Well, our prediction is based on only the single closest neighbor. That can be pretty risky, right? What if that one neighbor happens to be a total weirdo, an outlier? But if we set K to 5, Now we're getting a much more stable prediction. It's based on a democratic vote, a consensus. So choosing the right K is a huge part of making this model work well. Okay, let's switch gears and look at our second approach, which thinks in a completely different way. If K and N is kind of like asking your social circle for advice, this next model, which is called naive Bayes, is a lot more like a detective, carefully weighing all the evidence and just playing the odds. So instead of measuring distances like K and N does, naive Bayes is all about probabilities. It looks at a new observation and it asks, okay, based on all these features I'm seeing, what's the probability this is a type A versus, say, a type B? It literally calculates the odds for every single possibility and then just goes with whichever one is the most likely. This is a fantastic way to see how it thinks. So imagine the model is trying to figure out if something is a cat. It looks at each clue by itself. Does it have whiskers? Okay, that definitely increases the probability it's a cat. Does it meow? Whoa, okay, very likely a cat now. But does it weigh 100 kilograms? Probably not a cat. Naive Bayes just combines the probabilities from all these separate clues to make its final call. So why do we call it naive Bayes? Well, it's because it makes this one huge simplifying assumption. It assumes that all the clues are totally independent of each other. So in our example, it assumes that having whiskers has nothing to do with whether an animal meows. Now, in the real world, that's not always true, is it? But this naive shortcut makes the math way, way easier, and you know what's funny? It works surprisingly well in a ton of real-world situations. So, we've just looked at two completely different ways a machine can learn. One thinks about the world in terms of distance and groups, kind of like finding its crowd. The other thinks in terms of evidence and probability, like a detective solving a case. And this brings us to what I think is the most important takeaway of all. At the end of the day, machine learning is not some single magic bullet solution. It's a huge toolkit filled with all these different strategies. The real art, the real skill, isn't just knowing how one model works. It's about looking at a problem and knowing which way of thinking, whether it's geometric or probabilistic or something else entirely, is the right tool for the job. And that kind of leaves us with a really fascinating question to think about, doesn't it? We've taught machines to copy some of our own ways of reasoning. But as we get better and better at this, what other ways of thinking, maybe ways that are completely new to us, could we teach them? What other problems could we solve? Something to chew on. Thanks so much for joining me.